Springer, and this is R-2000, the Better Built House. Over the course of the last few programs, we've been looking at design and construction practices that can increase the structural performance as well as the energy performance, the key ingredients of the Better Built House. We worked our way up. We looked carefully at foundations, then we looked at walls, then we looked at the windows and doors that go into those walls, and now here we are almost on the roof. And at the roof, we're going to look at construction detailing that can add up to lower fuel bills and higher comfort levels. Now, all along, we've been relying on Oliver to give us the builder's viewpoint on energy-efficient housing. And since I don't particularly like my viewpoint right here, here's Oliver.
Come on up, David. It's beautiful.
Looks great, but I'm okay here. I'm happy.
You can see the whole project from here. It's amazing.
Oh, don't get me wrong. I like roofs. I like sloped roofs and peaked roofs and all kinds of roofs. I even have a roof on my house, but I don't like coming on roofs.
A lot of guys say this is the best part of the job. It's sunny, you take your shirt off. This is what building's all about. Come on.
Oh, that's what it's all about. Well, maybe in a couple of minutes. Right now, rather than come on the roof, I think I'd rather see a review on the control of heat losses in R-2000 homes.
The Better Built House incorporates design and construction techniques intended to provide the homeowner with increased comfort and reduced fuel bills. In pursuing these goals, the builder will attempt to keep labor and material costs to a minimum. The framing techniques will be designed to minimize heat transfer from the inside to the outside and will allow for high levels of insulation. The performance of the insulation materials installed will be optimized through good installation practices, and heat flows into and out of the house will be minimized by using airtight construction practices.
You know, Oliver, I probably don't really have to come up on the roof. I mean, you've shown me in detail all about the rest of the house, and probably the same thing up here, just more attention to detail, good installation practices, that sort of thing. And then you're going to tell me to put a bunch of insulation in the attic, which everybody knows anyway.
Well, okay, you're missing a great view, but the point is this. I'd like to find out if you know why we put more insulation in attics.
I guess because Mommy told me to wear a toque when it was cold out, and I put insulation in the attic for the same reason.
Sort of. The fact is that you don't insulate your attic more heavily than any other part of your building from an energy conservation standpoint. It's rather that it's very inexpensive to put in there. So it's an easy place to either add insulation if you're living in an existing home, or for a builder to put into a new house.
Well, what is different then in the attic?
Okay, you have to be concerned about the stack effect. It's really the only building science issue that we have to look at here. Do you remember what that is?
Well, you had a pretty fancy demo, but as I recall, it boils down to the fact that warm air rises.
You got it. And with that warm air goes a lot of humidity. So you want to make sure that there isn't going to be moisture entering your attic as a result of the stack effect or leakage in the vapor barrier at the ceiling. So you're going to be putting in a continuous sheet.
Well, so you're saying if you're going to have a humidity problem, the attic is likely where you're going to have the problem, so you have to be extra careful.
You bet.
Well, what about the fact that the attic is vented and cold and wind blows through it? Are there any concerns about that? Any changes you make for the R-2000 house?
There are two things that we should look at there. One is that you want to make sure you don't get that convective flow through the insulation. The second thing is that you do want to have the attic vented, and we're going to be looking at some baffles that will enable us to do that. We're also going to be looking at high heel trusses. So maybe we ought to go down into the attic and look at the trusses, since I can't get you to come up here.
Maybe we ought to go down in the attic. I think that would feel a lot safer than this. So you made me crawl up into a roof to see some minor alterations. They certainly look minor to me. Where are they?
Well, what I wanted to show you was this distance here. You'll notice that the top chord of the truss, or the rafter, if you will, has been spaced away from the top plates of the wall. What that enables us to do is to get a full depth of insulation over the top plate right at the outside edge. We've got a real good R value in the exterior wall. We've got a real good R value back in the rest of the attic. If you don't take care of this area and ensure that you get good insulation, you can have thermal bridging through the top plate.
So that's a pretty simple change to a truss. Does that mean trusses are your favorite? Are you limited to truss roofs?
By no means. There are an awful lot of other options. Let's take a look at some. There are several ways of providing higher insulation levels at the eaves. The high heel truss is the more commonly accepted route. Alternatively, you can raise the rafters by nailing a plate over the ceiling joists and then using metal fasteners from the rafters to the joists. That obviously allows an increased amount of insulation at the eaves. Of course, flat roofs and cathedral ceilings can be integrated into the design of energy-efficient houses. Innovative truss options for cathedral ceilings would include scissors trusses, parallel cord trusses, and lightweight products like plywood and metal web truss joists.
Well, all these systems are designed to bring on higher insulation levels. Can you take us through the system as it's being used in this house?
Well, let's look at the insulation options.
Well, Oliver, you know, I feel that I owe you for a great many things, but I'm going to have to add one thing. I owe you for the most terrifying climb into an attic I ever made.
Well, I'm really sorry. Take a good close look around, because we're probably the last people who are going to see this attic, and that's the reason we come in the gable end. We've completely eliminated putting attic hatches in our houses because there's so much insulation up here, nobody's going to be coming up here at all.
And I guess getting rid of the hatch solves you a problem for potential leakage and things, too.
You've got a continuous vapor barrier. You take the opening and put it outside, in a garage, gable end, something like that.
Okay, why are you using fiberglass up here?
Because it's cheap. What we want to do is use an inexpensive material, because in this kind of attic, we can put in as much insulation as we want. So the less expensive it is, the more we can put in. You'd either be using cellulose, fiberglass, anything that's inexpensive and easy to install.
This is, let me guess, one of those things I'm getting familiar with. It's up to the preferences of the builder, the region you're in, and what you like working with.
With one exception. If you're looking at a flat roof or a cathedral ceiling, you may find yourself using rigid board insulation, which is somewhat more expensive because the space that you have available to you is more limited.
So, how do you decide what R value to put in here?
Well, generally in North America, in the northern areas, you're going to be looking at something like R40. But if you really want to get scientific about it, you're going to take it back to the R-2000 program, use a computer simulation, and find out what the heat load calculation on the building is and make your judgment on that.
Or, alternatively, just load it in here if you got the space.
Can't do you any harm.
Now, when we were talking about installing insulation everywhere, you not only install it nice and fluffy and no gaps, but you want to prevent wind from blowing right through it. And this attic is kind of drafty. What do you do about that?
Well, this attic is outside the house. We don't have any wind blowing through the insulation. It's simply blowing through the attic itself. We've got these vent baffles down here at the eaves all around the building because we want to vent this space. Not so much to remove humidity that may be lost up into this area from the house, because of course we have a continuous vapor barrier, but more simply to cool the roof surface, especially in the summer if you're using something like black shingles, because it substantially enhances the longevity.
So I only have one question left. Do you think we could get down out of here now?
I think you'll like the next house we're going to, David. It's got no attic at all.
Gee, I guess common English terms mean something different to builders. This doesn't look like an atticless house to me.
Well, it isn't. It's a quasi-atticless house, if you will. What I want to point out to you is this bottom cord. Now, we were previously standing on these cords in a drop cord attic. It's possible to raise those cords so that you can give the effect of a cathedral ceiling from the bottom, from underneath, while still having lots of room for insulation here because the roof slope is really at a different pitch.
How far can you take this idea? How dramatic of a cathedral ceiling can you achieve?
Very dramatic. You can actually continue to raise this bottom cord until it in fact starts to run parallel to the top cord, at which point we call it a parallel cord truss, and still leave yourself lots of room for insulation in there as well as ventilation. That technology would be either parallel cord, or occasionally we use a term called truss joists if we're using a different interior plywood member, and that kind of thing can be used in flat roofs as well.
Well, now, you make it seem so simple, your concept of just raising that bottom cord up to make the ceiling. Does it change anything about the way you put in the vapor barrier?
Well, there's one very interesting thing here, because we, of course, are on the second floor of this segment of the building, while this area has got a cathedral ceiling. So it means that the vapor barrier in this case has to come over this ceiling and then actually go through this wall to come to our side of it, because we're inside the house and the attic is cold. We want the vapor barrier on the warmer side. So it means that the builder in this case has taken the vapor barrier down the wall, underneath this bottom plate, and all the way up in here, and this particular wall section is actually breathing to the outside through this Tyvek into the attic.
So this little section of wall has the honor of being an interior-exterior wall?
Sort of.
Now, what about ceiling penetrations and things like that? Are they all the same with a cathedral ceiling?
Well, you have to pay particular attention to them, as always. Let's go back to the other house and take a look. This is where the plumbing stack passes through the air barrier in a house, and it can pose real serious difficulty for the builder of these kinds of buildings because it moves.
Well, I like the way you have all this trivia. Why does it move?
Partly because of differential settlement in the building. The house is actually shrinking a little bit as it dries out, but mostly because you could have, say, 6 feet away from the plumbing stack a bathtub full of hot water, and when you pull the plug, all the hot water runs down, and it actually causes the pipe to elongate.
So you need some sort of a joint that can move but still retain that air tightness. What kinds of things do you use?
Well, your first alternative is to try and keep the pipe from moving at all, and there are expansion joints that are available, but they're very expensive. So what we find we use most often is to cut a very small hole and either use a single component polyurethane foam, or the best thing that we found is a neoprene gasket. Same kind of thing you use in roofing shingles, but you actually apply one where this plumbing stack passes through the air barrier, and you get movement there. It's still nice and tight.
Well, if hot bath water can make the stack move enough to be a problem, what happens with a chimney?
Very different circumstance. Let's take a look at that. This chimney is called a zero clearance chimney. But despite the fact that it's zero clearance, you still have to leave 2 inches between it and any framing members. So what you do there is to use a fire stop spacer. The fire stop spacer is used to actually take the place of the air vapor barrier. We're going to hold back our framing members around the chimney, bring our poly to those framing members, and then cut the remainder out to let the chimney pass through, and let this piece of sheet metal take the place of the air vapor barrier.
Well, it's all very nice and neat, Oliver, but what do you do with this great big crack that's left over?
You're either going to address that using something like muffler cement or a high-temperature silicone, which actually works a bit better because it stays flexible.
So are flues of various kinds and plumbing stacks the big penetrations to worry about in ceilings?
Those are the big ones, but we still have electricals. Well, David, you'll notice if you look up here on the underside of this ceiling that the ceiling has been strapped. As a result of that, we're able to run electricals in that strapping space without violating the air vapor barrier in exactly the same way as you can on walls.
Would there be any reason to strap the ceiling and not the walls, or vice versa?
Well, often guys will strap ceilings just in order to equalize the trusses because you get a better drywall job.
Ah, so that comes along for free. Now, what about polypans? Would you ever use something like a polypan in the ceiling?
Sure do. We particularly use polypans where you're looking at recessed fixtures because you have to be very concerned about overheating with all that insulation above there, and you've really got to watch that very closely. Another alternative for guys who don't want to strap or use polypans is to use these shallow boxes, which can either be surface mounted on the underside of the drywall and then covered with a fixture, or alternatively, because they're only a ½ inch thick, they can be set right into the drywall. Wherever a wire runs into it, though, you've got to caulk it very carefully.
That's great. So basically, ceilings are a lot like walls for electrics.
Same thing.
I think we're running out of time, and I think we better summarize pretty quickly.
You want to do that back on the roof?
You know, I'd love to do it on the roof, but since the crew had to carry me up there kicking and screaming, it took 3.5 hours to calm me down. I think we don't have enough time. I'm going over here.
Okay. Well, David, aside from reinforcing your fear of heights, how have we done?
Well, let's see. We saw that there are a variety of design and construction techniques that will allow you to get more insulation up into the roof, and paying particular attention to the eaves.
Okay. What about the insulation itself?
Comes down to good installation practices. Make sure it fits, is nice and fluffy, not compressed. But in particular in the attic, watch out that the ventilation system you're using doesn't blow cold air right in through the insulation.
Okay, and we want to reduce thermal bridging.
Oh, yes.
Remove the attic hatch, the whole shot. Okay, then lastly we looked at penetrations. Of course, the attic hatch is one of those. We looked at plumbing, we looked at chimneys, how to deal with those openings wherever you have them. I guess that's about it.
Yeah, I had a good time.
So when do you start your roofing company?
I don't think the roofers of the world have anything to fear from my competition. As a matter of fact, I'm looking forward to the next program where we're going to look at the mechanical systems in the better built house. Most of them are a lot closer to ground level. So join us.